All right, welcome. In this video, we're going to go over some basics on solutions and the forces that determine whether or not a solution will form. So whether or not something will be soluble in another substance. And we've got here some textbook references. Solutions are covered in chapter 4, and then either chapter 12 or 13. If you're looking at the hard copy, it's chapter 12. If you're looking at the e-text, it's a different version, it's chapter 13, just so you know. And in this video, we're going to be looking at these topics and just going over what are solutions and just looking at some different representations of solutions and thinking about the interactions between the components of a solution. And first, let's go over some definitions. Solution is a homogeneous mixture of two substances. And homogeneous means it's evenly mixed. So if you were to zoom in and look at one part of the mixture, and then you're to zoom in and look at a different part of the mixture, they should look about the same. So it's evenly mixed throughout the whole thing. In that solution, the one that you have more of, we call the solvent. And the substance that you have less of is the solute. So that's how you figure out solvent, solute. It's just whichever one there's more of, we call it the solvent. And then an aqueous solution, or you can call it aqueous, whatever you prefer, is the solution where water is the solvent. And remember, the symbol for aqueous is this. You put AQ by it. So if you say like salt water, you'd write NaClAQ, show it's dissolved in water. And this is the thing that we're most familiar with. When we think of solutions, you probably often think of dissolving a solid in water, like maybe you're picturing dissolving salt in water or dissolving sugar in water. And the ocean is an example of a solution. And the ocean is salt water, and it's mainly water. So water is the solvent. And then there's some salt in there, so that's the solute. Notice how the salt particles, so we could say that the ocean is, aqueous sodium chloride. And notice that the sodium chloride actually splits apart into ions. So we will find that that is something that ionic compounds do when they dissolve, is they actually split apart into the separate ions. There are other types of solutions you can have though. So remember, solution just means homogeneous mixture. So there's all sorts of stuff you can have. So you can actually have a gas dissolved in a gas. So like the air you're breathing right now, you can think of it as a solution of oxygen dissolved in nitrogen. And I say it's dissolved in nitrogen because nitrogen is the majority component. It's around like 70% nitrogen. So you can think of that as the solvent and oxygen being your solute. There's different types of liquid solutions we can have. You can dissolve a gas in liquid, a liquid in a liquid, or a solid in a liquid. You can even have a solid dissolved in a solid. So alloys are actually examples of solutions as well. Here's an example of an aqueous gas solution. So this would be carbon dioxide dissolved in water. This is how we get our carbonated beverages. And again, it's mainly water, so we consider water to be the solvent. CO2 would be the solute. Let me put those vocab terms here below so we can practice with those. Solute, solvent. And here's an example of showing how an alloy is basically some solids that are evenly mixed in together. And in some cases, this is kind of an interesting FYI, the concepts of solute and solvent are kind of not very useful. In this example right here, you can buy like 50% rubbing alcohol at the store, and that's a mixture of equal amounts isopropyl alcohol and water. So saying who's the solvent and who's the solute would be very arbitrary. So just kind of, it's a fun FYI to think about. And now let's talk about why some things, when you put them together, they form a solution, and sometimes they don't form a solution. So when we're considering like why solutions will form or will not form, it's important to know that there's a natural tendency of things to kind of mix together and get mixed up. And this has something to do with entropy, which we will talk about later on when we get into thermo, which I think is unit 6. So more on that later. But for right now, just notice that things will tend to spontaneously get mixed up. So mixing will occur spontaneously unless the substances are restrained somehow. And that could be either by a physical barrier, like in this example down here, we see on the left, we've got two solutions separated by a barrier. If we remove that barrier, then they're going to mix together spontaneously and form an even mixture. Or more likely what we're going to see is that if substances are not mixing, it's because there's some intermolecular forces that are kind of holding them back, that are preventing them from mixing. And here's some examples of intermolecular forces in the context of mixtures. So, for example, we got heptane and pentane. They're both nonpolar. They experience dispersion forces. Acetone, chloroform, they're both polar. They experience that dipole-dipole attraction. Ethanol can hydrogen bond with my water molecule over here. And here's where we will see ion dipole forces is in solutions. That's the only context we will see these. And this happens when you have an ionic compound dissolved in a polar or mixed together with a polar substance such as water. And if we're thinking about why, some solutions form and some don't, we want to think about the forces that might be, either preventing them or from forming or enabling them to form. So there's three kind of forces, kind of interactions that we need to think about. So in order for a solution to form, and let's kind of use the example of salt again. So you're going to have your solid salt, you're going to have your water, and then you're going to mix them together to get salt water. You can see there's kind of like three things here. So first you have to consider what we call the solute-solute attraction. So you have to consider salt attraction kind of to itself, right? Then you have to consider the solvent-solvent attraction, which in this case would be water. So like consider the attraction between water molecules. And then these are forces that have to be overcome in order for these to mix together, right? So in order to mix the salt and water together, first you have to separate those salt particles from each other, separate these water particles, then you're going to put them together and form this new interaction, which is what we call the solvent solute attraction here. So, and this is a kind of visual showing what's going on here. And let's take a look at this example more clearly. So we're looking at salt dissolving in water. So the solute-solute force that's like within the salt itself would be the ionic bond. So that attraction between the sodium and chloride ions in salt. The solvent-solvent attraction would be the hydrogen bonding that water molecules experience with each other. And then the solute-solvent attraction, so if we can successfully mix them together, then we will observe an ion dipole attraction between the salt ions and the polar water molecules. And we observe that, sodium chloride does in fact make a solution. So that means that this attraction of the ions to the polar water, so this like ion dipole attraction is like sufficiently strong to overcome that attraction of salt, sodium and chloride ions to each other. So we're kind of comparing these two relative forces. And here's kind of visual showing what happens when ionic compounds dissolve in water. So when your ionic compounds dissolve in water, this crystal lattice breaks apart into individual ions. And when you're noticing what's going on here with this ion dipole attraction, notice that if you're looking at your negative ion, you see how let me draw this out over here, that the positive end of your water molecules are attracted to the negative ion. And then it's the opposite for the positive ion. So remember, opposites attract. So the negative side of water is going to attract the positive cation, and the positive side of water is going to attract the negative anion. Okay. And this attractive force is known as an ion dipole force here. And this is what enables ionic compounds to conduct electricity when they're dissolved in water, is because they break apart and form these ions. So there's kind of charged particles moving around, and that's what allows electricity to flow. So not all ionic compounds are soluble. So let's look at an example of something that's not soluble. It's like silver chloride, turns out it's insoluble. You stick it in water and it just sits there. And if we look at these forces here, it's the same kind of forces we're considering. So the solute-solute attraction is the ionic bond, the attraction between the silver and the chloride ions. The water molecules are attracted to each other by hydrogen bonding. And then the solute-solvent attraction would be ion dipole. But in this case, they actually don't mix. So what that tells us is that the solute-solute attraction must be stronger than that ion dipole attraction. It's like there's something holding these ions back and preventing them from mixing with the water. So it must be that this silver chloride attraction is kind of like too strong, so they're not going to break apart and form a solution. So up next, we're going to explain the solubility of various substances using these intermolecular forces. So we'll talk about, are all ionic substances soluble? We already saw, no, they're not. Are all polar substances soluble or non-polar substances soluble? We want to be able to explain relative solubilities of substances based on their IMFs. Because even within a category of things that are soluble, you could be very soluble or just a little bit soluble. So you want to use those forces to explain what's going on there.